Honorable laureates, distinguished colleagues, ladies and gentlemen, welcome back and welcome to the Nobel Lectures in Chemistry for 2025. So, this year's Nobel Prize in Chemistry represents the remarkable accomplishments of building what you see here, molecular hotels, or even molecular residential buildings. Ordered structures where small atomic or molecular guests or residents can move in and out freely, thereby enjoying the accommodation space inside for their various needs or interests. These molecular hotels, or metal organic frameworks, or MOFs, as they are now called, they are the manifestations resulting from addressing very important challenges in chemistry. These structures show that such ordered structures can be predictably designed and synthesized, yielding extended multidimensional structures filled with spacious rooms or cavities. This development also shows that such porous structures can be designed to persist chemical or physical stress without collapsing, and that the frameworks can house important chemical processes, such as, for example, catalysis. Moreover, these discoveries demonstrate that such ordered structures can undergo dynamic changes upon demand. Our three laureates, our three master molecular architects or molecular builders, Richard Robson, Susumu Kitagawa, and Omar Yagi, they found truly efficient solutions to creating these spectacular and often visually very, very pleasing and appealing constructions. They could thus realize such multi-compartment molecular hotels by the ingenious assembly of judiciously chosen building blocks, metal-based components acting as nodes, and organic molecules acting as wall-building linkers. These discoveries have undoubtedly made the strongest impact on science and our society. For example, leading to the development of many, many thousands of MOFs, which have been designed for a very large variety of applications across many different areas. So, let's start with our first laureate. Richard Robson was born in 1937 in Glasburn, which is in the northern part of England, in the UK. He was awarded a PhD, a degree, from the University of Oxford in 1962, and relatively shortly after, he moved to Australia, where he has had a long career as professor at the University of Melbourne, where he is still also active. So, by this, please join me in welcoming Dr. Robson up on stage.
I think we're ready to go. Well, first of all, I'd like to thank the Swedish Academy and the Nobel Foundation for this award, and it's very much appreciated. I'd also like to congratulate the co-laureates, Susumu Kitagawa and Omar Yagi, on their awards, and and for their massive contribution to this area. So this notion of pre-organization has been at the underlying practically everything I've done since I've been an independent researcher. The idea that you can build chemical functionality and geometry into species that predisposes them to do things you intended them to do. Nature uses pre-organization to construct enzymes that perform fantastic chemistry, all a result of the pre-organization. Here are some of the pre-organized systems we played around with in the 1960s, 70s, and 80s. And play is the right word. It really was for fun. Highly irresponsible to use public money for private entertainment, but that's truly the way it was. So if you look at the bottom left there, there's a pre-organized bimetallic system where all sorts of unusual chemistry occurred, a result of that pre-organization or design. Practically everything I've done has been based on that notion of pre-organization. So in 1974, I was given the job of building ball and stick models of some basic inorganic structures like sodium chloride, zinc blende, wurtzite, and a number of others. And it was whilst constructing, putting the models together, fitting the rods into the wooden balls, that with the thought of pre-organization in the work we were doing at that time at the back of my mind, that the thought arose, what if we substitute the balls by pre-designed units and the rods by appropriate chemical bonds? Coordination chemistry was the area I'd worked in practically all my life, and it was ideally suited for this sort of exploration. So that idea sat around in my mind for a number of years, and in the middle 80s I roused myself to start doing something at the bench, and I looked for the simplest arrangement I could think of, which was diamond, in which every carbon atom is connected to 4 others at the corners of a regular tetrahedron. And a characteristic structural motif is the adamantane unit, which you see there at the top in blue. 4 cyclohexane rings fused together. That's characteristic of the diamond structure. Like a kid with big ideas and no real sense, I decided to aim for this molecule here on the left. An obvious thing for a coordination chemist to do, with acetal classical metal binding sites at each of the 4 termini. And this work was done in isolation and was not at all encouraging. I got minute amounts of this molecule, not enough to play around with metal ions. And so eventually I had to abandon that and turn to something much more mundane. The tetracyano compound there on the left, which was an unknown compound, but I was able to make sufficient quantities for metal binding studies. And the intention was to combine this with copper in the oxidation state 1. On the right there, you can see the tetraacetonitrile complex. So copper 1 has some sort of special affinity for nitrile donors. The intention was that every ligand would take on 4 coppers at the corners of a regular tetrahedron, and every copper would take on 4 separate tetranitales, again at the corners of a tetrahedron. And I was able to get crystals for crystallography, and Bernard Hoskins, my colleague, was able to solve the structure, and it was almost exactly as we intended it to be on the left there. Most unusual at the time. It was quite definitely crystalline, but the ordered part was less than 50% of the volume of the structure. Just a few words about Bernard. He was an old-style gentleman, and we were close friends and collaborators for 40 years until he died in 2002. He was a meticulous scientist, and all that space unaccounted for really bothered him, and I had to twist his arm a bit to get him to agree to publish it. In that report in 1990, on these there was a couple of diamond structures there. We also put forward a much wider ranging possibility of making a large number of different sorts of compounds. So a number of suggestions were made for where coordination polymer chemistry might go in the future. First suggestion was there's an almost limitless range of compounds you could make, quite from an organic chemist point of view, quite simple compounds. You could imagine some sort of molecular center with, say, 3 arms projecting outwards, or 4 arms going to the corners of a square, or 4 arms going to the corners of a tetrahedron, or 5 arms or 6 arms. And at the termini of each of these arms, you could put a whole host of different metal binding sites based on nitrogen, of which there are hundreds and hundreds of options there. Nitrogen, oxygen, or sulfur. So the number of combinations was just enormous, and that was apparent in 1990. And it was obvious that if you could get coordination polymers in crystalline ordered form as easily as I'd got that diamond structure with copper, you can appreciate the enormous range of possibilities. Second suggestion was that we could possibly make compounds with huge spaces between the framework components. Thirdly, it might be possible to introduce catalytically active sites into the individual building blocks, either before you put the structure together or afterwards. And quite a lot of research has been done in this area by others recently. Fourthly, it might be crucial that the bond-forming step be appropriately reversible. So that if a wrong step is taken, it can reverse itself. You can imagine an ordered structure, units clicking together in an ordered fashion in the intended manner, and then something goes wrong, and things start to get tangled up. And if the process is sufficiently reversible, then that could be disentangled, and the orderly build-up could continue. So I'd been working with shift bases for 2 or 3 decades at this stage, and I was well aware that CN, C double bond N formation is a reversible process. And there were 1 or 2 other examples of carbon-oxygen and carbon-carbon bond-forming steps that were reversible. So in this 1996 article, I was discussing the importance of reversibility in obtaining truly crystalline coordination polymers, and added that there wasn't any obvious reason why you couldn't do the same thing, not with metal to ligand bonds, but with carbon, oxygen, carbon, nitrogen, and so on, to produce truly crystalline 3-dimensional polymers. And it's been a great pleasure to me to see the development of the Koch area along these lines. Fifthly, ligands with chelating sites at the termini of the arms would give significantly more stable and robust structures. That was just obvious to a coordination chemist. In 1991, I was invited to a meeting of the American Chemical Society in Atlanta. And the proceedings of the meeting were written up subsequently as in book form in the ACS Symposium series. The Chemical and Engineering News reported on that meeting, and it was gratifying to see one of our coordination polymers on the cover of that issue. Not the cover of Time magazine, it's true, but still very encouraging at the time. So at that meeting, we put forward a general approach for the first time, I think. The first step, of course, is to choose a target. Second step is to devise building blocks with appropriate chemical functionality and geometry to aim towards that structure. And thirdly, and not trivial by any means, is to find ways of using the components you've made to generate crystalline material. Just to illustrate that point, that initial diamond structure, for example, was obtained in a not completely straightforward way. We had our source of copper-1 quite stable to air oxidation in acetonitrile solution. And this tetraphenylmethane derivative here was a big block of stuff and not very soluble in most organic solvents, but it was nicely soluble in nitrobenzene. So acetonitrile boils at about, 70 degrees or thereabouts. Nitrobenzene getting on for 200 degrees. The acetonitrile is much more volatile. So you could take this copper solution and this nitrobenzene solution of the tetraphenylmethane, mix them together, get a homogeneous solution, allow it to evaporate, and the acetonitrile is preferentially lost, and the nitrile of the tetraphenylmethane can increasingly compete with acetonitrile for copper, and hopefully, if you're lucky, you get crystals, and it turned out in this case that I did. So this is a list of the simple potential targets we could go for. We've already seen we need tetrahedral building blocks to get a diamond structure. And some of the others I'll mention as we go along. So alpha polonium is just a convenient name for this way of connecting things together in 3 dimensions. It requires octahedral units. So this is a representation of the alpha polonium structure. Every node is connected to 6 others at the corners of an octahedron. 1 above, 1 below, 1 to the left, 1 to the right, 1 in front, 1 behind. And this dipyridine unit here was something, even in those days, you could buy. And that was, for me, always an advantage not to have to make things. So we were interested to see if we could use this with various metal ions to generate an alpha polonium structure. I was able to get crystals suitable for crystallography very simply from aqueous solution with zinc and the 4,4-bipyridine. And the outcome was not a 3-dimensional structure, but a 2-dimensional sheet structure. It wasn't a surprise at all. Pyridine itself, in forming complexes, very rarely indeed takes on 6 pyridines per metal. This arrangement here with a water molecule above and a water below is much more common. So that it wasn't a big surprise. That report in 1990 was followed by a large number of other reports of polymers using 4,4-bipyridine, and one of them was this copper bipyridine coordination polymer, which I mentioned because it was the first coordination polymer to be referred to as a MOF. This combination of trigonal and octahedral components to give what we hope might be a rutile structure was of interest right from the early days. So here's a 50-year-old model of the rutile unit cell. The essence of the connectivity is centers attached to 3 other of the other type at the corners of a near equilateral triangle, and other centers that are attached to octahedrally to 6 of the first type of center. What we needed in those early days were building blocks that were simple, readily available, and stable. The simplest I could think of was this tricyanomethanide, intended to bind 3 metal ions at the corners of an equilateral triangle. Stuart Batten, who's present today, was the first student to work in this area. And Stuart was able to make a whole series of different metal derivatives of TCM, and they did have the rutile connectivity, which may not be so apparent in this representation here, but is more clearly obvious here, where we've got rutile itself, and this is the zinc coordination polymer. You can see identical connectivity. This ligand dicyanoamide also generated rutile structures where each of the 3 nitrogens could bind a metal ion, and it did form a rutile structure seen here to compare with the rutile itself above. And cobalt and nickel and copper derivatives of that ligand were obtained. The interesting thing about the cobalt-nickel compounds was that they behaved as ferromagnets at low enough temperatures. In other words, we were getting cooperative electronic interactions through the entire network. And this has always seemed to us to be an area of application that could well turn out to be more important than practically any other. This is a combination here, tetrahedral and square planar. So these are 2 nodes that are connecting, one going to the corners of a square, the other to the corners of a tetrahedron. The parent is platinum sulfide, which we see here. So the mauve platinum centers, all of them equivalent, are connected to 4 sulfurs at the corners of a square, and every sulfur is attached to 4 platinums at the corners of a tetrahedron. So initially we looked for the simplest components we could find, preferably nice and stable ones. And tetracyanoplatinate, an easily obtained, very stable entity, was an obvious choice. Under the simplest conditions, I was able to get crystals from a source of copper 1, the tetracyanoplatinate, and an appropriate countercation, which in this case was tetramethylammonium, and obtained crystals very simply indeed, and they did have the platinum sulfide connectivity. Right from the outset, using porphyrins as the square planar component was the exciting possibility for me. And so here we've got a tetrapyridyl porphyrin it has a metal which we don't want to be involved in the coordination chemistry making the polymer. So I chose to make the palladium derivative there, so that this center was essentially dead, and copper 1 as the tetrahedral component. And I was able to get very small crystals that Bernard was not able to do a single crystal structure on, but he did obtain a unit cell, and it was almost exactly what we calculated ought to be the case for a platinum sulfide arrangement. And then PhD student Diane McHale was able to use the copper tetrapyridyl porphyrin, much easier to make in larger quantities, and was able to make a number of platinum sulfide networks. And this is a representation of one of the compounds that Diane made. I don't think any chemist in 1994, when this was published, could see something like that without realizing the enormous potential that the approach had. Diane was able also to use a bigger square planar connecting unit with cyano-phenyl units in place of the pyridyls, putting the coppers, getting on for 4 angstroms further apart. And she was able to grow crystals which turned out to have 2 platinum sulfide networks interpenetrating each other and stuck together very closely by attractive porphyrin to porphyrin interactions. And that doubled up framework occupied less than 30% of the volume of the crystal. So we have platinum sulfide itself here, the tetracyanoplatinate derivative, the tetrapyridyl porphyrin derivative, the tetracyano-phenyl porphyrin derivative, and all of those are, have the same topology, exactly the same connectivity. And that sort of sequence or process, if you like, was given the name isoreticular expansion later on, and framework construction was referred to as reticular synthesis. So the simplest, most symmetrical 3D structure you can get with tetrahedral connecting units is diamond, as we've seen. The 3-connected analog of that is really interesting, and the simplest way of doing that is in the so-called 10-3A network, which I'll explain shortly. And as a target for construction, it was very attractive to us. So here's 10-3A itself. The 10 means that the shortest circuits that you can find in the structure are 10-gons. And that's one of the characterizing features of a particular topology. The 3 means that the nodes are 3-connected, and the A means that it's the most symmetrical of a number of 10-3 networks that can be imagined. It's has cubic symmetry and is chiral. So here you can see, but chiral, I mean, it's not superimposable on its mirror image, and that leads to interesting consequences. But here you can see helices, in this case counterclockwise, running from front to back. All the helices are equivalent. If you look from the side, you could trace here entirely equivalent helices, or if you look from top to bottom, likewise down here. So it has cubic symmetry, but is chiral. So this is the possible arrangement we're looking at in our general plan of doing things. This is an interesting ligand, hexaazatriphenylene, abbreviated HAT, which has the potential to bind 3 metal ions at the corners of an equilateral triangle. And we realized that if you have an octahedral metal ion and you attach 3 bidentate attachments, that the metal itself becomes a 3 connecting center. So these blocks of stuff here are heading out towards the corners of a equilateral triangle. So the metal itself becomes a 3 connecting node. And postdoc Patricia Jackson was able to make some hat, which wasn't entirely straightforward in those days, spent a lot of time making this, and found that she could get crystalline silver derivatives that did have the 10-3A connectivity. So all the ligands were equivalent to each other, and the ligands and the metals are both 3 connecting centers. So here you can see a hat ligand with 3 purple or mauve metal centers attached at the corners of an equilateral triangle, and all the metals are equivalent to each other. Each metal is chelated by 3 separate hat ligands at the corners with their centers at the corners of an equilateral triangle. And so there's one of the tengons can be seen here, but you can find tengons all over the place in this structure. So by the late 90s, this pre-organized building block approach was pretty well founded. And I think what our work in the 90s showed that it would be possible to make a essentially unlimited number of coordination polymers with designed structures and topologies. Around the start of this century, enormous numbers of reports started to appear on coordination polymers. And that process seems to have continued. I retired in the sense the university stopped paying me in 2004. And I've been slowing down ever since. And I've just been completely unable to follow this outpouring of stuff. Finally, a few acknowledgements. My wife, my daughter, and my son for their love and support. And these 2 gentlemen, Bernard Hoskins and Brendan Abrahams, who did all the, together with the students they supervised, they did all the real science, came up with hard numerical facts. Any scientific respectability in the papers we put out is due entirely to these 2 gentlemen and the people they worked with. And the people on the right here are the ones who did all the work, and it's a great pleasure for me to see most of them here in Stockholm at the moment. So once again, I'd like to thank the Swedish Academy and the Nobel Foundation for this marvelous honor, and I thank you for your kind attention.